We're back, ready to go with two-term expressions. Okay, two terms, if they're squares, they're easy. If you remember the two terms with cubes, that's the ones that we struggle to keep straight. So we'll see what we know here. The first question is, are all four of these two-term expressions possible? And the answer would be no. So my first question is, anybody remember which one is not possible to factor? And that answer would be yes, the one with the plus sign is not possible. When it's a difference of squares, we call a squared minus b squared a difference of squares. We know it unfoils, and actually it unfoils with conjugates. It's really, really nice. We know it has to be a and a to make a squared. It's got to be b and b to make b squared. And if we do one sign of each, the plus and the minus, we know we get the negative in the middle. The middle terms cancel. A squared plus b squared doesn't work because you have to use two plus signs and you can't get the middle terms to cancel. So you can never do squared terms that are added. It's not possible. Okay, if you look at these two examples I have down below, you'll go, okay, x squared minus 9. Both of those are perfect squares, and they're subtracted. So yes, we can factor that quite nicely with x and x, 3 and 3. We know one's got to be a plus, one's got to be a minus. The middle terms will cancel, so all things are good. What about x squared plus 25? X squared plus 25, they're both positive. There is no way, even if you try it, if you don't believe me, we'll try it. You'd have to have x and x, you'd have to have 5 and 5, but it'd have to be plus signs. Well, there's no way 5x and 5x, outers and inners, are going to make a 10x. You do not get the middle term to cancel. This just simply is not a possible event. You can't factor squares that are added. Those two usually we factor quite nicely and have a little trouble with. It's the perfect cubes that drive us crazy. We'll see if some of you remember the chant from last year. Perfect cubes both factor, subtracted and added, but they factor as a binomial and a trinomial. Okay, the binomial part, you simply uncube them, take the cubes off. So that would be a minus b. Keep the same sign in the middle, you just take the cubes off. Now, the trinomial, the three-term part, hopefully you remember the little saying, square, multiply, square. Square, multiply, square. What does that mean? That means you take the first term you wrote down, take the a, and you square it. So you square the first term, then you multiply the two terms you wrote down, the a times the b. But you always have to do the opposite sign. So if this was a minus, that will be plus a times b. And then you square the last term. So by the last term, I mean that you need to square the b you have here. So negative b squared will become a positive b squared. And there is your perfect trinomial. Now, if you actually choose to distribute and FOIL it back together, you're going to get a cubed minus b cubed. It works. I know it's funky and strange. Now, some of you may be saying, but can't I factor that trinomial farther? And the answer is no. Even if you try to take that trinomial farther, you can't get it to work. It will never break down more than this. So you don't have to try on this particular rule. The only difference between that rule and the a cubed plus b cubed is a change of signs. Since it starts with a plus, you start with a plus. Then it's still square, multiply, square. Square the a, multiply the ab, square the b. The difference would be, though, if the first sign is a plus, then the first sign in the trinomial is a minus. Those two are always opposite. Last one, because you squared it, it's always a positive. You'll never have a negative back there. Now, we need to try that with some that have actual real numbers, because for some reason, this is one of the hardest factoring methods that people have. I recopied the formulas over here already, so you have the formulas in front of you. We're just going to try to work a few problems. So, you look at this first bottom left one, 8m cubed plus, that's supposed to be, whoop, that's a typo, that is supposed to be 125. And you'll notice 8 is 2 cubed, that's perfect square, or perfect cube, excuse me. 125, that's 5 cubed, that's perfect cube. You see the m is cubed, so it should be screaming at you, hey dude, I'm the cube girl. So we're going to have a binomial and a trinomial. Okay. In the binomial part, you have to uncube it. So what number are you cubing to get 8? 8 is really 2 cubed, so we're going to write a 2 there. And of course it'd be m that we're cubing. So I'd have a 2m. 125 is nothing more than 5 cubed. So you'll have a plus 5. Once you get that part figured out, the rest of it is the square multiply square. So square the 2m. What do I get when I square 2m? I get 4m squared. Then you multiply the two things you wrote here. 2m times 5 is 10m. But you have to do the opposite sign. And then lastly, you square the 5, which would be plus 25. So you've squared, multiplied, square. And there's your solution. Once again, that trinomial is not going to factor farther, so you don't have to try. That's the cube rule. Okay, want to look at a couple of these here. 75x squared minus 12, that's 2 terms. So, okay, looking at our rules, is it perfect squares or perfect cubes? Well, it says x squared, so we're supposed to do squares, but 75 and 12 are not squared numbers. What do I do with 75 and 12? I notice that, 3 is in common. If I take a 3 out, I'll have 25x squared minus 4. And now look, 25 is a perfect square, 4 is a perfect square. So consequently then, I can simply do my nice easy 2 binomials. I'll have 5x and 5x. I'll have 2 and 2. And we know it's always one with a plus and one with a minus. You do need to leave the 3 out that front because that's part of the factors though. You don't just drop the 3 off. The 3 actually stays there as part of the factors. Okay, the last one here on this page is kind of sneaky because you're going, well, okay, it's b squared. It's a difference of squares, but 5 is not a square. But you can actually do this even if it's not by being kind of mean, sneaky, and nasty. It really will break down with our 2 conjugates. We know it's got to be b and b. We know it's got to be plus and minus. The question is, what do I use to make 5 that's the exact same number? Well, this is where it gets sneaky. What times itself makes 5? Square root of 5 and square root of 5. And so if you FOIL that back together, you'll still get b squared minus 5. So you can actually use this with numbers that appear to not be perfect squares, and they really are. Okay, the last method the book wants to include, and I'm not super fond of it, I call this quadratic form. The book calls this U-Substitution. And it does appear on the final, so we need to talk about it. Quadratic form is equations that follow the pattern of a quadratic, but they're not identical to a quadratic. You work them in the same style, but they don't quite have the same end point, I guess. If something's in quadratic form, it's in the form that follows a normal quadratic equation. Normal quadratic equations are something like x squared plus 2x minus 8. Okay, notice that you have x squared The middle term is x to the first. That's half of x squared. 1 is half of 2. And then you have a constant number. So if you have other equations that follow that same pattern, for example, if you have x to the 6th plus 2x cubed minus 8, it's still the same pattern, and you can still solve it by factoring like a quadratic, because the 3 is half of 6. So this is going to work. Okay, what would it have to be if I gave you x to the 20th? It would have to be 5x to the what? To be in quadratic form. Well, the 20 is 10. It'd have to be 5x to the 10th. And then, of course, you need an appropriate number that would help hopefully come out to get you the 5 in the middle. In this case, 14 would do the trick. All of those are in quadratic form and are therefore factorable. Okay, I will show you what the book means by U-substitution. On one that like this, x to the 4th with 7x squared, I wouldn't bother to go through the elaborate U-substitution process. I would simply go, oh look, it's a trinomial. The middle term is half of the first term. So it's got to be factorable. It's got to be x squared and x squared. And then you simply need to go, okay, I need factors of 44. Well, the obvious ones would be 4 and 11. And you need to check, can I get outers and inners to make a positive 7? Well, this is 4x squared. Outers are an 11x squared. And I believe 11 minus 4 is 7. So if I had a positive 11 and a negative 4, I could make this happen. Now, the thing is, you are frequently not done when you have these higher powers. Look at those two factors. Can they go farther? Their binomials are two-term expressions. They're squares. So squares can only be factored if they are perfect squares, a difference of perfect squares. You have to be subtracting. So that means, yeah, this first one, that can go farther. X squared minus 4 goes down to a good old x plus 2 and x minus 2. Now, x squared plus 11, we said the plus version is not factorable, so that just stays x squared plus 11. But you wouldn't be completely done with this problem until you had gone that far. So you should always stop and look at what you think may be your answer and see, can I go farther? Because a lot of times you can. Okay, this last one we're going to do, this is the U-substitution thing. This is in what we call quadratic form. I have something squared, something to the first power, and a constant. What the book suggests you do is that you make that whole quantity, rather than a quantity, just make that u squared. And so n plus 5 over here is just u minus 21. I don't know why mathematicians like the letter u for substitution, but we use it a lot. So now, is that factorable? 3u squared minus 2u minus 21? Well, that's a trinomial. That's 3 terms, so that means we're just unfoiling. To make a 3, I have to have a 3u and a 1u. 21, I'm guessing it's probably 7 and 3. Anybody else want to take a shot? You think it's going to work with 7 and 3? And the question is where to put the 7 and where to put the 3. If I put the 7 out here, the outers are going to make 21. That looks awfully big. So I would hazard a guess that my 7 is not the right thing to do. And unfortunately, it's moving when I want to erase. So we'll see if we can back that up a little bit. So clearly what I have there is not going to work. So what do you suggest we do? Well, we just need to simply reverse it, try the other direction. So if I had put the 7 on the inside and the 3 outside for the 21, now do my outers and inners work? There's 7u. On the outside I have 9u. To get a negative 2u, I would need a negative 9 and a positive 7. That works because I'm going to have one of each sign, and that I know negative 21 needs one of each, so I'm going to have a plus 7 and a minus 3. Now, the question is, are you done? And the answer is, of course, no. We substituted that in. We replaced those quantities with u so we could find it easier to factor. But now we've got to take it back to where it came from. So now we have to go back and go, oh, okay, I have a 3, but instead of a u was really n plus 5. So now I have 3 times n plus 5, and then of course my plus 7. And the same thing here, I have to replace that u with n plus 5, and then I have a minus 3. So I've actually factored with quantities. You think that's a simplified answer? I sure hope you're saying no. So now we need to clean it up. I'm going to distribute the 3, which will give me 3n plus 15 plus 7. And over here, I can add up, that'd be n plus 2. Now in the first term, I still have more numbers I can combine, so I could make that 3n plus 22 and n plus 2. And so while that seemed like a crazy and wild thing to factor in the first place, you can handle situations like that with what's this called U-substitution. If you can work it, if you could have gone straight to this step down here, you could have gone from the very beginning to this and just factored it with n plus 5, so be my guess, that's fine, if that works for you. But if you need to substitute the u in so you can see what you're factoring, go for it. Do whatever makes you be successful. That concludes our chapter R review, or our chapter R review chapter. And so once you finish this assignment, you will be ready for a review sheet and a fun and exciting test. Good luck with factoring.